Imagine a power source that is virtually limitless, produces almost no long-lived radioactive waste, and uses fuel extracted from seawater. It's the energy that powers the stars, and for decades, scientists have been trying to bring it down to Earth. This is the promise of nuclear fusion. In simple terms, nuclear fusion is the opposite of nuclear fission, which is what powers our current nuclear plants. Fission splits heavy atoms. Fusion merges light atoms. We typically use two isotopes of hydrogen, deuterium and tritium. When these two nuclei are forced together at incredibly high speeds and temperatures, they overcome their natural electrical repulsion, fuse, and form a heavier nucleus, helium, releasing a massive amount of energy in the process. The key takeaway? The resulting helium atom weighs slightly less than the two original hydrogen atoms combined. That tiny bit of missing mass is converted directly into pure energy, following Einstein's famous equation, E equals mc squared. Fusion isn't science fiction. It's happening right now, 93 million miles away. The Sun is a giant natural fusion reactor. Inside its core, the immense gravitational pressure and temperatures, around 15 million degrees Celsius, are enough to force hydrogen nuclei to fuse. It's a perfect, self-sustaining system. If the Sun can do it, why can't we? Because replicating the Sun's conditions on Earth is one of the greatest engineering challenges in history. To make fusion happen here, we need to heat the fuel to temperatures even hotter than the Sun's core, over 150 million degrees Celsius. At that heat, the atoms break down into a superheated, electrically charged gas called plasma. The problem is, no physical material on Earth can contain something that hot. If the plasma touches the reactor walls, it instantly cools down, and the reaction stops. We need a perfect, non-physical container. Scientists have developed two main ways to solve this confinement problem. 1. Magnetic Confinement (MCF). This is the most well-known approach, using a device called a Tokamak. A Tokamak is a donut-shaped chamber that uses incredibly powerful magnetic fields to trap and suspend the superheated plasma. It's like a magnetic bottle, keeping the plasma away from the walls. The largest and most ambitious project of this type is ITER, the Way, a massive international collaboration in France involving 33 nations, designed to prove that fusion can produce more energy than it consumes. 2. Inertial Confinement, ICF. The second approach is inertial confinement. Instead of magnets, this method uses powerful lasers, hundreds of them, to rapidly compress and heat a tiny pellet of fusion fuel. The goal is to squeeze the fuel so quickly and intensely that fusion occurs before the pellet can fly apart. The U.S. National Ignition Facility, NIF, is the most famous example of this technique. The stakes are enormous. Successful fusion would mean a clean, safe, and virtually inexhaustible energy source for humanity. The fuel is abundant. Deuterium can be extracted from ordinary water. And unlike fission, there's no risk of a runaway chain reaction. We are closer than ever. Research has advanced key performance parameters by a factor of 10,000 over the last 60 years. ITER is expected to achieve its first plasma in the 2030s. The dream of harnessing the power of the stars is slowly but surely becoming a reality. Nuclear fusion is a testament to human ingenuity, a quest to solve our energy needs by mimicking the cosmos. It's a long, difficult road, but the payoff could change the world forever. What do you think? Will fusion power our future? Let us know in the comments below. And if you want to see more science explained simply, hit that like button and subscribe to the channel.